Our study of kinematics is going to take us into 2 dimensions. And before we can get started in that study, we're going to have to learn a little bit more about vectors. Some of this we've already done, so I'm going to go through it pretty quickly. And in particular, that's going to be our vector properties, but some of them are going to be new. So just as a refresher, keep in mind that a vector is nothing more than a number with a direction. And in 1 dimension, there are only 2 possible directions, left and right, up and down, in and out. But there's only 2 ways you can go in 1 dimension. So we generally will designate the direction using a plus sign or a minus sign, at least mathematically, because that's how you show opposite whenever you're doing math. If you're just talking about cardinal directions, if you want to show the opposite of east, you write it as west, for example. Now, where it gets to be a little different is that in 2 dimensions, you're given a magnitude, but you're not given a minus sign, ever. You're always given a reference angle. So they tell you how long the arrow is, and then they tell you what direction the arrow points. So our first property that we're going to look at is the fact that a vector has no absolute position in space. It has no home. So the big thing is that you have to maintain size and orientation. What I mean by that is this. If I call this vector A, then vector A can exist here, it can exist here, down here. It doesn't matter where I put it. Vector A is still vector A just as long as I maintain the size and orientation. Now, if I were to change the direction of that, I no longer have vector A. It's often going to be necessary to do vector subtraction. And in order to do vector subtraction, we just need to think of subtraction as being addition with the opposite. So before we had vector A, which looks like this. If I want the opposite of vector A, then I'm going to maintain the same magnitude. I'm just going to have to change the direction. And so in terms of arrows, that means this is going to be vector minus A. Now, some of the other mathematical properties that we're going to see with vectors are this. We have A plus B. If we have just 2 separate vectors, generically A and B, that will be the same as B plus A. If we have vector subtraction, that's going to be vector A minus vector B is not the same thing as vector B minus vector A. But vector A minus vector B would be the same as vector A plus a negative vector B. Very often in physics, we get to multiply vectors by scalars. And the name scalar really means just that. Its purpose is to scale a vector up or down. It changes the size of your vector. It doesn't change the direction, just the size of it. For example, we could say that we have a vector delta V is equal to vector A times t. So our change in velocity is equal to AT. Remember that this equation comes from V final minus V initial is equal to AT, or V final is equal to V initial plus AT, and that's our velocity function. All right, now, returning back to what we have here, if you look carefully, you can see that this is our vector, and this is going to be our scalar. And if I want to know what the change in velocity is, then it's going to be the scalar times the vector, so I can rewrite that as t times a. Now, if we're going to do this with arrows, then I'm going to have to draw a vector, and we'll say that this is vector A. And if I assign an arbitrary value to time, let's say time is equal to 2 seconds, then delta V is going to be equal to 2 times vector A. So that means I need 2 of these arrows. And so what I'll do is this. So now we have A, vector A, and vector A once again. 2A, that's just like saying I've got A plus A. So the resultant vector is that. So this is delta V, which is also equal to 2 times vector A. Everything we're doing here is all very conceptual, and doing vectors with diagrams and arrows is extremely beneficial when you're just trying to get the big picture. In which direction does my vector point? Or my final answer, is it supposed to be? Is it going to be a large answer, a small answer? Does it point up and to the left, or is it straight right? So this helps to give you a sense of what's going to be correct and what's going to be incorrect. This year we're going to spend a lot of time working with vector components. And basically a vector is something which can be broken up into a right triangle, and we've got 2 legs to a right triangle, and then we have the hypotenuse. The hypotenuse of our triangle is the vector itself. You know, for example, we've been talking about vector A. But the legs of the triangle, those are going to be the components of vector A. And so what we have is this. Here's vector A. It just points up and to the right. A is composed of 2 components. One which points horizontally, so this we would call vector AX. So this is AX. And then there's a component which is going to be vertical, and that's going to be vector AY. It's these 2 components which combine to form this vector. This is going to be very important for working in 2 dimensions, because all the equations that we work with are going to be established for 1 dimension only. And if there's a secret to doing anything in 2 dimensions, it's recognizing that you basically have 2 one-dimensional problems. And so it's extremely important to be able to take this vector and look at that part of the vector which lies only in 1 dimension or the other dimension. Because what we're going to learn is that these 2 dimensions are independent of each other. If I change 1 dimension, that has no bearing on what happens in the other dimension. So if we just label this diagram very quickly, this is our vector. This is the vertical component, and this is our horizontal component. Very often we'll have vertical and horizontal components for our vectors, but that's not always going to be true. What is always going to be true is that the components of a vector are always at right angles to each other, and they form a right triangle where the vector itself is the hypotenuse. So the longest line in this triangle is always the vector itself. Vectors are, we said, in 2 dimensions. Vectors are usually given a reference angle. So they'll tell you the magnitude and the direction, but it's a reference angle. So for example, we can call this angle theta. So if I want to determine what the size of AX is, then I'm going to have to use trigonometry. And everybody's learned SOHCAHTOA. And we have the sine is equal to the opposite over the hypotenuse, and the cosine is equal to the adjacent over the hypotenuse, and the tangent function is equal to the opposite over the adjacent. And we're going to use this a lot this year. Now, in my particular example, I've used the x-axis as my point of reference for 0 degrees, and therefore theta is being measured from the x-axis. So if I want to know the x component of this vector, then now this is the adjacent side of the triangle, this is the opposite side of the triangle. Remember that adjacent and opposite are in reference to theta, the angle that you want to use. So if I use this theta here, then this side is opposite and this side is adjacent. If, on the other hand, you were to be given this angle, and we'll call that one beta, now this side, AX, is opposite of this angle, and AY is adjacent to the angle. So we have to be very careful, and we have to pay attention to which angle is being referenced. So in this case, if I want to find the x component, then the x component is going to be found using the cosine function. So we get cosine of theta is equal to the adjacent over the hypotenuse. Now, using the variables of our diagram, the adjacent side we're calling AX, and the hypotenuse we're calling vector A. Therefore, AX is equal to A cosine of theta. Now in the y dimension, it's the same thing. We get sine of theta is equal to the opposite side over the hypotenuse. So we get sine of theta is equal to AY over A. So AY is equal to A sine of theta. Now, you don't want to get in the habit of always using cosine for the x and sine for the y, because there are many examples in physics where that's not going to be true. For example, when we study pendulums, we're going to find that the angle which is often given for a pendulum is in reference to a vertical axis. That's going to be our angle theta. And if you're looking for the x component, for whatever it happens to be, you can see that this is the opposite side of our angle, and so we're going to have to use the sine function. So just for sake of completeness, if we use beta as our reference angle, then the x component becomes a sine of beta, and the y component becomes a cosine of beta. Okay, here's a couple of examples that I would like for you to try on your own. Let's just say that you're given a force which has a magnitude of 80 newtons. The angle theta is given as 27 degrees, and I would like for you to find the x and y component of that angle, or of that vector. Okay, now remember that in order to get fx, we would be, and our angle is being referenced from the x-axis, and this is the adjacent side of our triangle. Fx becomes f cosine of theta. So fx is equal to 80 cosine 27 degrees. So fx is equal to, check your calculator, make sure it's in degree mode. And so we get 80 cosine 27. And so Fx becomes 71.3 newtons. Fy is equal to F sine of theta, which is 80 sine 27 degrees. So again, we go back to our calculator, and we get 80 sine 27, and that's going to be 36.3 newtons. Try this next example. The angle we're given is 10 degrees, and this is a displacement vector which is 10 meters long. Okay, so dx is going to be equal to, now let's draw in what we're looking for here. This is our y component right here, and this is our x component right there. You can see that x is opposite the 10-degree angle, so that's going to be the sine function. So dx is equal to d sine 10 degrees. So dx is equal to 10 sine 10, or dx is equal to 1.74 meters. dy is equal to d cosine of theta. So dy is equal to 10 cosine 10, or dy is equal to 9.84 meters. Okay, try another one. We have 240 kilograms meters per second. This is a unit of momentum. And the angle we're given is 60 degrees. Go ahead and calculate the momentum in the x dimension and the momentum in the y dimension. Okay, so we can see that our x component is this, our y component is that. If this is 60 degrees, this has to be 90, so this is going to be a 30-degree angle. And here's the thing, you have the choice. If you would prefer to use this angle of 30 degrees, you're welcome to. If you prefer to use the angle which was given, which was 60 degrees, you may do that as well, because the only difference is whether or not you're using sine or cosine, and it's not going to change your answer. And your reasons in any particular problem will vary as to whether or not you do or don't change it. It's just a personal preference. So that's 30 degrees. And let's do it using the 60 degrees, which is over here. Okay, so these are alternate interior angles. And so what we get is this. dx is equal to d sine of 60 degrees. So dx is equal to 240 times the sine of 60. So we have 240 times the sine of 60 degrees. That's going to be 207.8. So dx is equal to 207.8 kilograms meters per second. In the y dimension, dy, we have 240 cosine of 60. So dy is equal to 120 kilograms meters per second. Now, One thing that we haven't seen yet is the fact that this vector points to the left. And that's why it's important to be careful to actually sketch out these vector diagrams, because it makes it easy to see that the value for dx as written is incorrect. Remember that we're using a conventional coordinate system, and that means that dx must be negative. We have to indicate that that is to the left. And you're going to find throughout the course that the one thing that gives you the most problems from being successful is probably going to be the minus signs. Everybody makes mistakes with them. I still make mistakes with them. And so learn to embrace that and look for minus sign mistakes, because very often if you get the wrong answer, it's because of a minus sign. Now, dx is negative because it points to the left, but dy is still positive because it points up. And so we can have this mixture within our dimensions.